Good morning, students. I welcome you all in the MSc second year physical chemistry. So today we will see the photoelectron spectroscopy and applications to variety of solid surfaces. So I know last 3 months you are missing college and fun with your friends and the chemistry labs. So we will hope that India will be soon free from this COVID pandemic and you all can come to the college. So why we need to study this specific spectroscopy, that we will know the reason. First, when you buy the utensils from the market, it will look like this. But when we use it for some time, then it looks like this. So why is it so? As we all know, the surface oxidation of metal happens. So we need to prove this by using some of the techniques. So the X-ray photoelectron spectroscopy can be a good technique to prove these kind of concepts. So what are all the advantages of this spectroscopy? This in this spectroscopy, we can detect many elements in a single spectrum. As you can see in this figure, that here in this figure, chlorine, sulfur, phosphorus, silicon, aluminium, magnesium, and sodium. This all we can detect in a single run. So several elements can be analyzed in a single experiment scan due to characteristics binding energy of each element. So ISCA is nothing but electron spectroscopy for chemical analysis, and also called as XPS, was coined due to the application like this. So ISCA is a non-destructive technique, means the 100% of the sample can be recovered after the analysis. How and why the surface study needs to do? Analysis of surface boils down the surface sensitivity, that whether it is possible to detect the desired signal above the noise level. The sensitivity is a major problem in all surface studies. Consider the case of a sample with a surface size of 1 centimeter square having have and 10 to the power 14 atoms on the surface layer. In order to detect the presence of impurity atoms present at the 1% level, a technique must be sensitive to the 10 to the power 12 atoms. In contrast with this, a spectroscopic technique used to analyze a 1 centimeter cube bulk liquid sample, that is sample of 10 to the power 22 molecules. The detection of 10 to the power 12 molecule in this sample would require 1 ppt sensitivity. Very few techniques can provide anything like this sensitivity level. So this is the reason why common spectroscopy techniques such as UV, visible, NMR, which is having the detection limit of 10 to the power 9 molecules, cannot be used for surface study analysis. So introduction to photoemission. Photoelectric effect is the fundamental phenomenon of photoelectron spectroscopy. Indeed, the Nobel Prize was awarded to Einstein for explaining the photoelectric effect. The photoelectric effect demonstrated in 1905 and the Auger electron transitions by Perry Auger on 1923. So we state that H nu is equal to kinetic energy plus binding energy plus work function. Work function is nothing but first ionization potential in molecules and energy difference between EF and vacuum level on solids. EF is nothing but the Fermi energy level. First commercial ISCA was available only on late 1960, mainly due to the slow development of high vacuum technology and necessary electronics. So what is the photoelectric effect? As we all know, the photoelectric effect is the emission of electrons or the other charge carriers. When light shines on a material, electrons are emitted in a manner that can be called as a photoelectrons. This effect can be attributed to the transfer of energy from the light to an electron. The electrons are dislodged only by the impingement of photons when those photons reach or exceeds a threshold frequency or energy. Below that threshold, no electrons are emitted from the material regardless of the light intensity or the length of time exposure to the light. So what is photoelectron spectroscopy? As we know, the photoelectric effect, when we shines the light on the material, it ejects the electron. The electron can be ejected either from the core level or from the valence level. So the binding energy is equal, h nu is equal to binding energy plus kinetic energy plus work function. So if the electron ejects from the core level, it is called as the X-ray photoelectron spectroscopy. And if the electron ejects from the valence shell, it is called as a valence band photoelectron spectroscopy. So these both are called as a photoelectrons. So what is the main difference between the X-ray photoelectron spectroscopy and ultraviolet photoelectron spectroscopy? So in X-ray photoelectron spectroscopy, using the soft X-rays 200 to 2000 electron volt radiation, we can determine the core levels. By in case of ultraviolet photoelectron spectroscopy, using a vacuum UV 10 to the 45 electron volt radiation, we can examine the valence level. In case of XPS, the elements present on the surface and their chemical state like oxidation state can be studied. But in case of UVPS, the valence band hybridization, position of valence band maximum, ionization energy and work function can be studied. So, introduction to photoemission. So, X-ray photoelectron spectroscopy. This is the energy level diagram. In this, with this spectroscopy, we can also study the Auger electron emission. So, what is the difference between photoelectron emission and Auger electron emission? In the first case, you can see in the photo emission, when light shines on the metal surface, it ejects the electron directly from the core level. But in case of Auger electron emission, when light shines, it ejects the core level electron, but the electron from the valence shell falls down in the core level and ejects the electron from valence shell. So this is Kai M. Saiban in 1980 to 2007. He is the father of photoelectron spectroscopy and received the Nobel Prize in 1981 for his contribution towards the advancement of photoelectron spectroscopy. He worked in University of Uppsala, Sweden. So, introduction to photoemission. Meaning of photoemission: the kinetic energy distribution of photoelectrons produced by the ionizing radiation of a fixed frequency or energy. The photoionization will yield to a polychromatic or polyenergetic flux of electrons, which in turn monitors the discrete form of the electronic energy levels. The orbital energy levels of electrons within a molecule is obtained directly in a photoemission, in contrast to the absorption and emission spectroscopies, where the experimental transition and energies represent the differences in orbital energy. So, introduction to photoemission. Ionization potential and or binding energies are the characteristics properties of the atoms and molecules, and method provides for a direct means for chemical analysis, and hence the name ISCA, electron spectroscopy for chemical analysis. We can see here an example. For copper 2p3 by 2, the core level appears at 932 electron volt, and no other element contributes to the same binding energy region. So UPS and XPS analyzes the valence band and core level of atoms or molecules respectively, as we can see in this figure. In case of UPS, we can see the electron is ejecting from the valence shell, and in case of XPS, electron is ejecting from the core level. So X-ray photoelectron spectroscopy is a surface sensitive technique, and it is also a quantitative spectroscopic technique that measures the elemental composition at parts per thousand range, which can also measure the empirical formula, chemical state, and electronic state of the elements that exist within a material. XPS spectra are obtained by irradiating a material with a beam of X-ray while simultaneously measuring the kinetic energy and number of electrons that escape from the top 0 to 10 nanometer of the material being analyzed. XPS can be used to analyze the surface chemistry of a material in its as received state or after some treatment. In principle, XPS can detect all the elements after the atomic number 3, that is Z is equal to 3 from lithium and above, but it cannot easily detect hydrogen and helium. The detection limit for most of the elements on a modern instruments are in the parts per thousand range. The detection limits of parts per million are possible but require special conditions like major concentration at the top surface or very long collection time overnight. So XPS is routinely used to analyze inorganic compounds, metal alloys, semiconductors, polymers, elements, catalysts, glasses, ceramics, paints, papers, ink, woods, plant parts, makeup, teeth, bone, medical implants, biomaterials, viscous oils, glues, and modified materials, and many others. XPS is less routinely used to analyze the hydrated forms. So what are general applications of XPS? Elemental composition of the surface we can study from 0 to 10 nanometer. We can also study the empirical formula of materials. We can see if any contamination is there on the surface. Then chemical or electronic state of each element we can find at the surface. The uniformity of elemental composition across the top surface we can check, and uniformity of elemental composition as a function of ion beam etching also we can study by using this X-ray spectroscopic analysis. Thank you.